Hi, this is Kaitlyn.
Hi, I'm Lexi. Today we're going to teach you a little bit about Thermo.
Thermo! Okay, so this is the 2005 AP Chemistry Free Response, question 7, Form B. And the first question asks us to write a balanced chemical equation for the complete combustion of 1 mole of CH3OH. And when we're dealing with C's, H's, and O's as a reactant, we're always going to have O2 as a reactant and CO2 and H2O as a product. So then from there, all we do is balance. So first we're going to write out the reactants.
And that is for combustion reactions. That's important to keep in mind also.
So only combustion and C's, H's, and O's. So CH3OH plus O2 yields CO2 and then plus H2O. And so from here, all we do is balance. So we're going to have 2 waters because we have 4 hydrogens in the reactant side. So we need 4 hydrogens in the product side. So this is 4, 4. And so then oxygen is a little bit more difficult because we have 4 over here and we need to have 4 over here. So the only way we can do that is using a fraction. And so we're going to use 3 halves. And so now we have 1 over here and 3 over here. So that makes 4 oxygens and 4 oxygens. So that's it. Okay, so this problem up here, this is the equation that we found from the previous problem, part A. And so part B, they're asking us to determine the enthalpy change for the reaction C plus H2 plus H2O yields CH3OH. And so this is a Hess's law equation, so really what we're going to be doing is flipping or adding or subtracting equations to get to H2 plus C plus H2O yields CH3OH. And so what we do is we have H2 plus 1/2 O2. And then the enthalpy change for this one is 290. And then C plus 2. And then for this problem up here, we're going to have to flip it. Oh, I forgot to write this one. This is 390. We're going to have to flip it to get to what we want. The C plus H2 plus H2O yields CH3OH. So we have to flip this one. So what we're going to flip it to is CO2 plus 2H2. And remember, when you flip an equation, you have to change the sign. So now it becomes positive 730 kilojoules moles.
Maybe next time you don't sell me out to the town.
So, to follow through with Hess's law, we already took care of this equation, so I'm going to cross it out so we don't get confused. We flipped it down here, which is why it has a positive delta H now. So, we have 3 halves O2 on the product side, and that perfectly cancels out with 3 halves O2 on the reactant side. So we can cancel all of those out. Then we have CO2 on the product side and CO2 on the reactant, so that cancels. And we have 1 H2O, but we have 2 on this side, so we're left with 1 here. But we can cancel this one out. So then we just add what's left over. So we have H2 plus C plus H2O, because we only have 1 left, yields CH3OH. Then with the delta H's, we need to add what we have left over. So when we add 730 to negative 390 and negative 290, we get 50 kilojoules per mole for this equation. So that is the answer. So now we're on to part C. The problem asks, write the balanced chemical equation that shows the reaction that is used to determine the enthalpy of formation for 1 mole of CH3OH. That part's really important, the enthalpy of formation. We have to remember that the enthalpy of formation means only elements. and it says 1 mole of CH3OH. So we know it yields CH3OH. Now, we have to remember back to our diatomics in order to correctly do this problem. So if you've been taught before, a good way to remember your diatomics are Brinkelhoff. And we have carbon here, hydrogen, and oxygen. And hydrogen and oxygen appear in our Brinkelhoffs. So we know that they exist in pairs of 2. So we have carbon by itself, plus H2, because it's a Brinkelhoff, plus O2, because it's also a Brinkelhoff. And then now we need to correctly balance. We have 1C, 4 O's, so 2 O2, and then only 1 O over here. So here we have another fraction come into play, and we need 1/2 O2. And that's it.
Okay, so now part D, and I wrote the equation for H2 because it's kind of hard to see. So the question is asking us to predict the sign of delta S for the combustion of H2. And so we're going to be working with this equation, and I wrote it here. And delta S is disorder. And if you have positive delta S, then you have more disorder. And if you have negative delta S, then you have less disorder. So what you do for here is you look at the states of matter. H2 is gas. Oxygen is gas, and then H2O is liquid. And so we're going from gas to liquid, so gas to liquid. And when we go from gas to liquid, it's negative. And so it means when you have negative, you have less disorder. So then delta S is negative.
Because we're creating more order. Okay, so we're almost finished. The last part of number 7 is letter E. The question reads, on the basis of bond energies, explain why the combustion of H2 is exothermic. First, we need to remember what exothermic means. And exothermic means that heat is a product. And what's really important is that the delta H of an exothermic reaction is negative. And that compares nicely with our H2O equation, which has a negative delta H. Now then we need to pay attention to the words bond energies. Delta H, when we look at bonds, is actually calculated backwards compared to when we normally calculate it. So it's the bonds broken minus the bonds formed. And in that case, it would be reactants minus products. So when we look at our combustion equation, we have H2 plus 1/2 O2 makes H2O. And so looking at our delta H in terms of bond energies, the negative 290 value means that the energy that is formed from the bonds is greater than the energy that is broken from the reactants. So in that case, if we look at the equation, then the energy that is formed from the H2O is greater than the energy that is broken from the H2. So that's what we would say in our explanation. Hope that makes sense, and hope that you learned a little bit about Thermo. Thanks.
Thank you. Thermo rocks.